Hello everyone and welcome to lesson number 10, Networks and Telecommunications. For most businesses and organizations today, networks and telecommunications are critical parts of business infrastructure. Telephony is the field of technology that includes the development and deployment of services to support all electronic communications. Many organizations could not operate if their networks were unavailable or prone to error. Network security involves meeting an organization's essential need for network availability, integrity, and confidentiality. The data transmitted through the network is protected from modification, either accidental or intentional. It cannot be read by unauthorized parties, and its source and destination can be verified, which means non-repudiation. Business and security requirements are things like access control, network stability and reliability, integrity, availability, and confidentiality or non-repudiation. This lesson will examine how you can secure networks and telecommunications. It introduces the basic elements of a network and explains the security issues surrounding networks. It presents some of the building blocks for securing data as they travel through your network. As a security professional, you need to understand three elements of the networks and telecommunications world: the Open Systems Interconnection or OSI reference model, network topology, transmission control protocol or /internet protocol or TCP/IP, wireless networking, and network security. The learning objectives is to describe networking principles and security mechanisms. Key concepts include the OSI reference model and its security lapses, physical and logical network topologies, TCP/IP and how it works, network security risks and defense tools, and wireless networks and security controls. The Open Systems Interconnection Reference Model, or OSI model, is a template for building and using a network and its resources. The OSI reference model is a theoretical model of networking with interchangeable layers. The beauty of it is that you can design technology for any one of the layers without worrying about how the other layers work. You really need to make sure that each layer knows how to talk to the layers above and below it. This figure shows each layer of the OSI reference model. The OSI reference model layers are as follows. First, you have layer 7, or the application layer. This layer is responsible for interacting with end users. The application layer includes all programs on a computer that interact with the network. For example, your email software is included since it must transmit and receive messages over the network. A simple game like solitaire doesn't fit here because it does not require the network in order to operate. Next is the presentation layer. This layer is responsible for the coding of data. The presentation layer includes file formats and character representations. From a security perspective, encryption generally takes place at the presentation layer. Next down is the session layer. This layer is responsible for maintaining communication sessions between computers. The session layer creates, maintains, and disconnects communications that take place between processors over the network. Next is the transport layer. This layer is responsible for breaking data into packets and properly transmitting it over the network. Flow control and error checking take place at the transport layer. Number 3 is the network layer. This layer is responsible for the logical implementation of the network. One very important feature of the network layer, which I'm going to cover later in this lesson, is logical addressing. In TCP/IP networking, logical addressing takes the familiar form of IP addresses. Next down is the data link layer. This layer is responsible for transmitting information on computers connected to the same local area network, or LAN. The data link layer uses media access control, or MAC addresses. Device manufacturers assign each hardware device a unique MAC address. And finally is the physical layer. This layer is responsible for the physical operation of the network. The physical layer must translate the binary ones and zeros of computer language into the language of the transport medium. In the case of copper network cables, it must translate computer data into electrical pulses. In the case of fiber optics, it must translate the data into bursts of light. The OSI reference model enables developers to produce each layer independently. If you write an email program that operates at the application layer, you only need to worry about getting information down to the presentation layer. The details of the network you're using are irrelevant to your program. Other software takes care of that for you. Similarly, if you're making cables at the physical layer, you don't need to worry about what network layer protocols will travel on that cable. You just need to build a cable that satisfies the requirements of the data link layer. As a security professional, you'll learn a lot about networking. In fact, a good working knowledge about networks and how to secure them is crucial to protect your organization from network failure or a data breach. Many of the devices used in the security field protect networks. Those that don't protect networks often rely on them to function at least. In this lesson, we're going to examine the two main types of networks, wide area networks and local area networks, and explore their function. You'll also examine some of the ways to connect your LAN to a WAN. Finally, I'm going to give you a brief look at the most important network devices. Let's start with the wide area networks. As the name implies, WANs connect systems over a large geographical area. The most common example of a WAN is the Internet. As shown in this figure, the Internet connects many independent networks together. This allows people at different locations to communicate easily with each other. The Internet hides the details of this process from the end user. When you send an email message, you don't have to worry about how the data move. You just click send and let the network deal with all the complexity. From a security perspective, it's important to remember that the Internet is an open network. You cannot guarantee data privacy once data leaves your network. The data might travel any path to get to their destination. Anyone might be able to read those data along the way. Think of data on the Internet as more like a postcard than a letter in a sealed envelope. Fortunately, security technologies such as encryption enables you to hide the meaning of your data when you're sending it across the Internet. This is similar to sending a postcard but writing the message in a secret code. You'll learn more about network encryption later in this lesson. Most of today's organizations use the Internet to connect different locations to each other and to connect with their customers. This is a low-cost way to connect sites, since it is usually easy and inexpensive to connect the network to the Internet. However, you must make sure that you consider the security issues surrounding the use of an open network such as the Internet. Again, encryption technology can help you reduce the risk of using the Internet. Some organizations prefer to use their own private networks for connecting remote sites. Some choose to do so for security reasons. Others simply want to guarantee reliability of private networks. Although this is a very good option for security and reliability reasons, it is also very expensive. However, there's no reason you can't work with communications providers to develop your own private WAN. There are multiple methods you can use to connect to the Internet. Most home users choose either a cable modem, and that's old, or a digital subscriber line, or a DSL, from the telephone company. But these aren't the only options. Internet service providers, or ISPs, are increasingly providing high bandwidth internet service using fiber optics. This type of service provides much faster internet connections than previous service options. Users with no access to cable, DSL, or fiber optic service can still connect to the Internet using satellite or old-fashioned dial-up services. As internet use increases, ISPs add more choices to the way to connect. In many cases, the number of available options for connecting to the Internet depends on where you live. More densely populated areas tend to offer more options. You can also connect to the Internet through a wireless carrier. Advances in wireless technology make cellular connections affordable in many areas, and service area coverage increases daily. Smartphones generally connect to third generation, we call that 3G, or fourth generation 4G networks, and we also have 5G networks today. Many of these devices also have the ability to connect to Wi-Fi networks using 802.11 standards. Cellular 3G and 4G networks provide stable internet and voice communication over a wide area. The connections to the Internet seem to be continuous. However, the devices are actually moving from cell to cell. This handoff from one cell to another is invisible to you or to the users and make it appear as though connections are continuous. However, most cellular network carriers impose data transfer limits and charge fees for access when users exceed these limits. Mobile device users prefer Wi-Fi network connections due to the higher network speed and lower usage costs. It isn't difficult to find free Wi-Fi access at many coffee shops, hotels, and a wide variety of other locations. This ease of internet connectivity makes mobile commuting a real option for the average user. These cellular networks are very popular with individual users and businesses. Today's carriers currently offer devices for laptops and mobile access points. In fact, many smartphones and tablets can act as wireless access points for other devices. These mobile access points devices connect to the Internet using a cellular network connection and convert the connection to a Wi-Fi connection for capable devices. That means that you can connect a laptop, smartphone, and even several other devices to the Internet anywhere you're located in your carrier's coverage area. This ability can be a huge advantage over using free Wi-Fi. The internet connection speeds are generally slower using 3G or 4G wireless access devices. However, such connections are far more secure. You don't have to worry about sharing your internet connection at a coffee shop with an attacker on the same network. Most public Wi-Fi networks are very insecure. You never know who else is on the same network just listening to all your traffic. Sacrificing a little speed to get a secure connection may be worth it. Businesses also have many choices for internet service. Surprisingly, many of them are the same choices available to home users. For example, most ISPs offer business service in addition to their consumer offerings. This is often at a much higher speed than home connections to support the needs of business users. Of course, ISPs generally charge a premium fee for this increased speed. Think back to the OSI reference model that I just told you about for a moment. The important thing to remember is that the connectivity option you choose will not affect what you can do with your network. The differences relate to the way the signal gets into your building, telephone lines, cable lines, dedicated wires, and the speed and reliability of your service. A router is a device that connects two or more networks and selectively interchanges packages of data between them. A router connects a LAN to a WAN by examining network addresses to decide where to send each packet. The placement of a router within the network architecture affects configuration choices. You can place routers in two basic locations, and you can look at this slide in order to understand them. You can have a border router. A border router is subject to direct attack from an outside source. When you configure any router, you should determine whether it is the only point of defense or if it is one part of a multi-layered defense system. Of course, a multi-layered defense is far better and more secure. The lone defense router can protect internal resources, but is subject to attack itself. Next, look in the middle where you see internal routers. An internal router can also provide enhanced features to your internal networks. Internal routers can help keep subnet traffic separate. They can keep traffic out of a subnet and keep traffic in a subnet. For example, an internal router that sits between the network of an organization's research department network and the network for the rest of the organizations can keep the two networks separate. These routers can keep confidential traffic inside the research department. They can also keep non-research traffic from crossing over into the research network from the organization's other networks. You can configure routers to allow all traffic to pass or to protect some internal resources. Routers can use network address translation, or NATing, we call it, and packet filtering to improve security. NAT uses an alternate public IP address to hide a system's real IP address. One of the original purposes of NAT was to compensate for a shortage of IP addresses. Today, it helps with security by hiding the true IP address of a device. An attacker will have more difficulty identifying the layer of networks behind a firewall that uses NAT. Packet filtering is a function of a router or a firewall. It happens each time the router or firewall receives a data packet. The device compares the packet to a list of rules configured by the network administrator. The rules tell the device whether to allow the packet into the network or to deny it. If no rule specifically allows the packet, the firewall blocks the packet. NAT and packet filtering are two good ways to use your routers to help defend your network. They provide some defense against basic attacks. It is important to remember, however, that no single technology is a silver bullet. You should still use firewalls to protect your network and other technologies described in this program to secure your data. LANs provide network connectivity for computers located in the same geographic area. These computers typically connect to each other with devices such as hubs and switches. This switching infrastructure is located behind the organization's router, as shown on this slide. In many cases, systems on the same LAN do not protect themselves from each other. This is intentional, since collaboration often requires connections between LAN systems that you would not normally allow from the internet. This is why it's extremely important to have good security on systems located in your LAN. If a virus infects a system on the LAN and other systems do not protect themselves, the virus can spread quickly to all systems on the LAN. Until about a decade ago, many different types of LANs existed. Now almost every network has switched to a single technology called Ethernet. In early Ethernet networks, all computers connected to a single wire and had to fight with each other for turns to use the network. This was inefficient, of course. Fortunately, technology has evolved. Modern Ethernet networks use a dedicated connection for each system. This wire connects each system back to a switch, which controls the LAN. The Ethernet standard defines the way that computers communicate on the network. It governs both the physical and data link layers of the OSI reference model. Ethernet defines how computers use MAC addresses to communicate with each other on the network. Ethernet has become the most common LAN technology in use. Even many computing technologies now have variants that run on top of Ethernet. For example, Internet Small Computer System Interface, or ISCSI, is a storage networking standard used to link data devices to networks using IP for its IT transport layer. An alternative to ISCSI for both optical and electrical networks is fiber channel. Fiber channel was originally used in supercomputers to connect storage devices, but has since spread into common use across many types of computers. The fiber channel over Ethernet (FCOE) protocol makes it even easier to connect fiber channel capable devices to an Ethernet network. This is yet another example of the way layered network protocols make it easy to implement many different types of network devices. Two main devices connect on a LAN: hubs and switches. Hubs are simple network devices. They contain a number of plugs or ports where you can connect Ethernet cables for different network systems. When the hub receives a packet on any port, it automatically retransmits that packet to all the other ports. In this way, every system connected to the hub can hear everything that every other system communicates on the network. This makes the job of the hub quite simple. The simple nature of a hub is also its major disadvantage, though. A hub creates a lot of network congestion by retransmitting everything that it hears. In the last section, I told you about how old-fashioned Ethernet networks had every system connected to the same wire. When you use a hub to connect systems, you get the same result. Every system communicates with every other system on the network, making it difficult for a single system to get a packet in edgewise. This causes network congestion and reduces the speed of the network for everyone using it. Switches are much better alternatives to hubs. A switch performs the same basic function as a hub, connecting multiple systems to the network. However, switches have one major added feature. They can perform intelligent filtering. Switches know the MAC address of the system connected to each port. When they receive a packet on the network, they look at the destination MAC address and send the packet only to the port where the destination system resides. This simple feature provides a huge performance benefit. Switches are now inexpensive and have greatly improved performance. That's why almost every modern network uses switches to connect systems. Generally speaking, only small networks still use hubs. Virtual LANs or VLANs. A virtual LAN is any broadcast domain that is isolated from other domains. You create VLANs in the routers and switches configuration setup. A VLAN is a collection of logically related network devices that are viewed as a partitioned network segment. This gives administrators the ability to separate network segments without having to physically separate the network cabling. VLANs can be used to isolate logical groups of devices to reduce network traffic and increase security. For example, if you create a VLAN for your HR department, all sensitive information traveling from one HR computer to another HR computer is hidden from all non-HR computers. Now let's look at TCP/IP and how it works. Imagine a lunch table with a Chinese speaker, a French speaker, and an English speaker all talking to each other. That would be a very confusing conversation now, wouldn't it? The lunch guests must have one language in common if they want to communicate. The same thing is true with computers. Fortunately, almost every computer now speaks a standard language or protocol called the Transmission Control Protocol / Internet Protocol, or TCP/IP. A protocol is a set of rules that govern the format of messages that computers exchange. A computer protocol governs how networking equipment interacts to deliver data across the network. These protocols manage the transfer of data from a server to an endpoint device from the beginning of the data transfer to the end. In this section, I'm going to teach you about the protocols that make up TCP/IP and the basics of TCP/IP networking. TCP/IP is actually a suite of protocols that operate at both the network and transport layers of the OSI reference model. It governs all activity across the internet and through the corporate and home networks. The U.S. Department of Defense developed TCP/IP to provide a highly reliable and fault-tolerant network infrastructure. Reliability, not security, was the focus. This suite of protocols has many different responsibilities. This figure shows a portion of the TCP/IP suite. One of the primary functions of network layer protocols is to provide an addressing scheme. This layer contains the addressing scheme in TCP/IP. IPv4 or IP version 4 are 4-byte, which means 32-bit, addresses that uniquely identify every device on the network. With an explosion in the number of network devices during the end of the last century, it was clear that IP version 4 did not allow for unique addresses for each device. That's one of the reasons IP version 6 was developed. IP version 6 addresses are 128 bits long and can provide far more unique device addresses than the older standard. In addition, IP version 6 contains many additional features and is more secure. Adopting it is slow, however, and IP version 4 is still the most common IP addressing technique in use today. This figure shows the difference between the notation for IP version 4 and IP version 6 address. As you can see, IP version 4 addresses use the dotted quad notation, it's called. This represents each of the 4 bytes as an integer between 0 and 255. Each IPv4 address consists of a network address and a host address. For example, the IP version 4 address 192.168.10.1, which you see on the screen, is for the network address 192.168 and the host address 10.1. The dividing line between the network and host addresses can change based on the way an administrator configures the network. A network configuration parameter known as the subnet mask defines this dividing line for a particular network. All hosts that share the same network address are part of a subnet. A subnet is a partition of a network based on IP addresses. Since IP version 6 addresses are so much larger than version 4, IP version 6 uses a completely different notation. As seen again in this figure, IP version 6 addresses are expressed as hexadecimal values separated into 8 groups of 16 bits. Because every computer needs its own IP address, keeping track of address assignments can be time-consuming. Many organizations that use IP version 4 use Dynamic Host Configuration Protocol, or DHCP, within a network to simplify the configuration of each user's computer. This allows each user to get his configuration information dynamically from the network instead of the network administrator providing the configuration information to the computer. DHCP provides a computer with an IP version 4 address, subnet mask, and other essential communication information. It simplifies the network administrator's job. An example of DHCP communication appears here. Technically, DCHP works only with IP version 4 networks. DHCP version 6 provides IP version 6 addresses. Network application software needs to know the address of a remote device in order to establish communication with that device. The networking software stack handles all the details of getting the message from one device to another. Application software also needs to identify more than just the target address. The software needs to tell the receiving or target device where to send the messages once they get there. This destination address is called a network port. A network port is just a number that tells the receiving device where to send messages it receives. Client software sends network messages to specific ports, and server software listens to ports for incoming messages. For example, almost all unencrypted traffic between web browsers and web servers use port 80. Port 80 is commonly used for HTTP traffic. This table that you see before you lists ports that common services use. No one forces software to use the common ports, but most software uses standard ports to make it easy for clients and servers to communicate. You've already seen some of the most common network protocols. There are many more protocols that define communication rules for many uses. Although this list is not comprehensive, this slide contains a list of some of the more common network protocols you should recognize, as does this slide. Once you've configured all the network components, you need to monitor your network for health and performance. Internet Control Message Protocol, or ICMP, is a management and control protocol for IP. ICMP delivers messages between hosts about the health of the network. ICMP messages carry information on hosts it can reach, as well as information on routing and updates. Two ICMP tools are ping and tracer route. The ping command sends a single packet to a target IP address called an ICMP echo request. This packet is equivalent to asking the question, "Are you there?" The computer on the other end can either answer the request yes with an ICMP echo reply packet or ignore the request. Attackers sometimes use the ping command to identify targets for a future attack. Because of this potential vulnerability, many system administrators configure their computers to ignore all ping requests. The tracer route command uses ICMP echo request packets for another purpose, to identify the path that packets travel through the network. Packets may travel many different routes to get from one point on the network to another. The tracer route command displays the path that a particular packet follows so you can identify the source of potential network problems. Attackers can use ICMP to create a denial of service attack against your network. This type of attack is known as a Smurf attack, named after one of the first programs to implement it. It works by sending spoof ICMP echo request packets to a broadcast address on a network, hoping that the hosts on that network will all respond. If the attacker sends enough replies, it is possible to bring down a T1 from a dial-up connection attack. Fortunately, it is very easy to defend against Smurf attacks by configuring your network to ignore ICMP echo requests sent to broadcast addresses. Let's take a look at network security risks. Any data in transit are a potential attack target. This makes network security important. So far in this lesson, you learned about how networks carry data. You've also learned about a few risks facing networks, such as Smurf attacks and eavesdropping. In this section, I'm going to take you on an in-depth look at some network security risks. We'll also cover some of the network security controls that you can put in place to protect your network. Let's take a look at the categories of risks. There are three main categories of network security risks, and that's reconnaissance, eavesdropping, and denial of service. Each of these have different impacts on the availability, integrity, and confidentiality of data carried across the network. They also may affect the security of the networks itself. In this section, we're going to examine some of the most common network security risks. First, let's look at reconnaissance. Network reconnaissance is gathering information about a network for use in a future attack. Consider an army that wants to attack a country. The attacking army needs a lot of advanced information to succeed. Some of the things a commander might want to know are as follows. What's the terrain? What's the location of roads, trails, and waterways? Locations and types of enemy defenses, weaknesses in the enemy's perimeter, procedures for allowing access through the perimeter, and types of weapons used by the enemy. Similarly, a network attacker will want to know many things before attacking also, like IP addresses used on the network, or type of firewalls and other security systems, or remote access procedures, or your operating systems of computers on your network, or weaknesses in your network systems. Normally, you wouldn't simply make this information available to an attacker. Unfortunately, however, attackers have many tools to obtain it. You have already learned why it's important to block ICMP echo requests from outside your network. This block stops attackers from using the ping and tracer route tools to gather information. You also want to be sure to configure systems to provide as little information as possible to outsiders. This will limit the effectiveness of network reconnaissance attacks. Next is eavesdropping. Attackers also might want to violate the confidentiality of data sent on your network. Before you learn about network eavesdropping, consider a less complex technology, and that's your telephone. If you've seen a spy movie, you know that it's easy to tap a telephone if you can get to the telephone wires. You simply need to hook up a cable to the telephone switch box on the house and connect a handset to listen in on calls. Network eavesdropping is just as simple. If an attacker has physical access to a cable, he or she can simply tap that cable and see all the data passing through it. You have a few options to protect against this type of attack. You can limit physical access to the network cable. You can use switch networks. The attacker would then only see information sent to or from the computer attached to the tapped cable. You can encrypt sensitive data. Then the attacker still might be able to see the transmission, but won't be able to make sense of it. Network eavesdropping is easier than telephone eavesdropping. Physical access to the network makes it easier, but it's not required. If an attacker compromises a computer on the network, the attacker can use that computer for eavesdropping. Using switch network and encryption will help limit the effectiveness of this type of attack. You should also secure systems on your network from malicious code. Finally, we have the denial of service. Often an attacker is not interested in gaining access to your network. Rather, he or she simply wants to deny you the use of it. This can be an extremely effective attack tactic. Many businesses can't operate if they lose their networks. An attacker has two primary methods to conduct a denial of service attack: flooding a network with traffic and shutting down a single point of failure. Flooding a network with traffic is the simpler method. You can think of a network as a pipe. It can carry only so much data before it gets full. If you send it more data than it can fit in the pipe, the network becomes clogged and useless. Attackers can create a denial of service attack by simply sending more data through a network line than it can handle. One variation of this theme is a distributed denial of service attack. In this attack, the black hat hacker uses many systems around the world that he or she has compromised to flood the network from many different directions. It becomes difficult to distinguish legitimate traffic from attack traffic, and the network grinds to a halt. Distributed denial of service have been around for years. However, they are not considered old types of attacks. Attackers still use DDoS attacks to slow down or disable their victims. Back in 2012, a group of activists with hacking abilities called hacktivists launched a series of denial of service attacks against several major U.S. banks. Hacktivists are behind more and more large-scale attacks to attract attention, generally to some political issue. These attacks continued through 2012 and into 2013 and still continue today. The targets of these attacks included U.S. Bank Corp, J.P. Morgan Chase, Bank of America, PNC Financial Services, and SunTrust Banks. As the attacks continue, they affected more organizations. Some customers have been frustrated due to slow bank websites. Others were unable to reach their banks online at all. The ongoing attacks continued to disrupt online access to the bank websites, but often were not as successful as the earlier attacks. The banks were learning from the earlier attacks and added new controls to protect their websites. Previous attacks often focused on large retailers. Several major internet retailers, including Amazon.com, Walmart, and Expedia, were the victims of denial of service attacks since 2009. These attacks shut down all three websites for about an hour in the middle of the winter holiday shopping season. The companies lost revenues as customers turned to other retail websites, and things got even worse than that. In December 2014, an unnamed ISP reported an NTP reflection denial of service attack that generated a peak of 400 gigabytes of network traffic, a volume of traffic beyond what any ISP could have handled. Needless to say, the ISP's customers were unable to connect to the internet during this attack. Technology advances provide more opportunities for attackers to cause problems with denial of service attacks. A fairly new attack called a telephony denial of service, or TDOS attack, is starting to become more common. A TDOS attack attempts to prevent telephone calls from being successfully initiated or received by some person or organization. These attacks became more prevalent in early 2013. Attackers are targeting an increasing number of organizations that depend on telephone calls as a primary mode of communication. The result is similar to standard denial of service attacks. These network attacks that can disrupt or totally disable telephone communications can cause enormous impact on the business. Damage can include revenue loss, potential fines, the inability to conduct operations, and a loss of customer confidence. Protecting yourself against a denial of service attack can be difficult. The most obvious approach is to ensure that you have adequate bandwidth to withstand the load. Some new technologies on the market seek to defend against distributed denial of service attacks, but they are unproven and limited in their effectiveness. The best defense is to detect attacks as early as possible and take action to block the incoming traffic before it renders your network unusable. Here are those distributed denial of service attacks I talked about and the telephony dial-up service attacks. Let's look at some basic network defense tools that you can utilize. Defense against these kinds of risks that I talked about begins with some basic hardware and software tools, things like firewalls, virtual private networks, and network admission control. Let's start with firewalls. A firewall controls the flow of traffic by preventing unauthorized network traffic from entering or leaving a particular portion of the network. You can place a firewall between an internal network and the outside world, or within the internal network to control access, or within the internal network to control access to particular corporate assets by only authorized users. Firewalls are critical elements of networking security, but they are just that, elements. Firewalls will not solve all your security problems, but they do add a much needed deterrent. This figure shows the role of a firewall in the network. It separates private networks from the internet. It also separates different private networks from each other. In this section, I'm going to talk about the different types of firewalls and the roles they play in the network topology. Firewalls are powerful tools in securing networks. Since each firewall is configured using rules, they provide the most common way to implement rule-based management. Rule-based management is simply managing the security of a network by defining rules of what is acceptable and what's not. Firewall rules are filters defined in the firewall's configuration that make it easy to implement many of these security requirements. Different types of firewalls use different types of rules. Even the simplest firewalls support access control lists. An access control list simply defines a rule to handle traffic for one or more hosts using a specific protocol and one or more ports. In addition to just securing a host, firewalls can filter traffic based on ports, often simply called port security. Access control lists can contain very specific rules or may contain range of hosts and ports. Each rule tells the firewall how to handle certain types of messages. The most common actions are allow and deny. If you want to create the most secure network, you can configure your firewall to deny all messages except the ones that you explicitly allow. This approach is called implicit deny. It can be very secure, but it requires more effort on the part of the network administrators to open ports as needed. Firewalls can help secure networks in multiple ways. In addition to the filtering features you have already seen, firewalls can provide these security features as well. Flood guard. Rules can limit traffic bandwidth from hosts, reducing the ability from any one host to flood a network. Loop protection. Firewalls can look at message addresses to determine whether a message is being sent around an unending loop. This can be another form of flooding. And network separation. Filtering rules enforce divisions between networks, keeping traffic from moving from one network to another. The basic function of a firewall is quite simple. It must block any traffic that you don't explicitly allow. Firewalls contain rules that define the types of traffic that can come and go through your network. Each time the firewall receives a network message, it checks the message against its rules. If the message matches the rule, the firewall allows the message to pass. If the message does not match the rule, the firewall blocks the message. Going beyond this basic functionality, firewall technology includes three main types. First, you have packet filtering. A packet filtering firewall is very basic. It compares received traffic with a set of rules that define which traffic it will permit to pass through the firewall. It makes this decision for each packet that reaches the firewall and has no memory of packets it has encountered in the past. Next is stateful inspection. A stateful inspection firewall remembers information about the status of a network communication. Once the firewall receives the first packet in a communication, the firewall remembers that communication session until it's closed. This type of firewall does not have to check its rules each time it receives a packet. It only needs to check rules when a new communication session starts. And finally, you have the application proxy. An application proxy firewall goes further than a stateful inspection firewall. It doesn't actually allow a packet to travel directly between systems on opposite sides of the firewall. The firewall opens separate connections with each of the two communicating systems and then acts as a broker or a proxy between the two. This allows for an added degree of protection because the firewall can analyze information about the application in use when making the decision to allow or deny traffic. The type of firewall you choose for your network will depend on many different factors. If you're placing a simple firewall at the border of a large network, you may want to use a basic packet filter. On the other hand, if you're protecting a highly secure data center that hosts web applications, an application proxy might be more appropriate. You can deploy firewalls in many different ways on your network. In this section, I'm going to look at a few of the most common firewall deployment techniques: border firewalls, screen subnet or DMZ firewalls, and multi-layered firewalls. Depending on your organization's security needs, one or more of these approaches may be a good fit. Let's start with border firewall. The border firewall is the most basic approach. Border firewalls simply separate the protected network from the internet, shown in this picture here. A border firewall normally sits behind the router and receives all communications passing from the router into the private network. It also receives all communications passing from the private network to the internet. Border firewalls normally use either packet filtering or stateful inspection. Border firewalls are most common for organizations that do not host public services. If you outsource your website and email, you might not need to allow the public to get into your network at all. In this case, you may simply block most or sometimes all inbound traffic. A border firewall excels in this scenario. Next is the screen subnet. Often it's not possible for you to block all traffic into your network. If you host a public website or your own email server, you need to allow inbound connections on a limited basis. The screened subnet firewall topology, which you see here, is the best approach for this type of requirement. The firewall has 3 network cards. 2 are set up identically to a border firewall, with one connected to the internet and another connected to the private network. The third card connects to a special network known as the screen subnet or demilitarized zone, or DMZ. You see that at the top. The DMZ is a semi-private network used to host services that the public can access. Users have limited access from the internet to systems in the DMZ to access these services. A secure network does not allow direct access from the internet to the private network. This approach recognizes that systems accessed from the internet pose a special risk. They are more likely targets of attacks and therefore are more likely to suffer successful attacks. If you confine these machines to the DMZ, they can jeopardize only other systems inside the DMZ. An attacker who gains access to the DMZ system would not be able to use that system to directly access systems on the private network. I'm going back to this diagram to take a look at multi-layer firewalls. In large and/or highly secure environments, organizations often use multiple firewalls to segment their network into pieces. This is the case that's illustrated here. In this figure, one firewall acts as the border firewall, protecting subnets A, B, and C from the internet. However, two other firewalls separate subnets B and C from each other and from subnet A. Multi-layer firewalls are useful when you have networks with different security levels. For example, in this figure, general users may connect to subnet A. Users working on a secret research project might connect to subnet B. Executives might connect to subnet C. This structure provides the secret project and the executives with protection from the general user community. Unified threat management is the next thing I want to cover. Firewalls are so important to network security that they have matured into devices that do far more than just packet inspection. In fact, multi-purpose firewalls are more commonly referred to as Unified Threat Management, or UTM, devices. UTM devices do provide filtering as well as many other security services. Some of the services UTM devices provide include these. URL filter. This feature filters web traffic by examining the URL as opposed to the IP address. Content inspection. The device looks at some or all the network packet content to determine if the packet should be allowed to pass. This type of inspection can help identify malicious content from trusted sources. This could happen if a trusted source is compromised. And finally, malware inspection. A specialized form of content inspection. The device looks at packet content for signs of malware. These unified services make it possible to reduce the number of devices that must analyze network packets. Fewer UTM devices can provide the same level of security as many more older devices. However, even with fewer devices inspecting packets, introducing UTM devices often slows down a network due to the sheer amount of work that devices must accomplish. It takes time to inspect and analyze each network packet and multiple layers of the network stack. For this reason, some organizations have elected a middle-of-the-road approach. A web security gateway accomplishes some of what a UTM device does, but without all the overhead. In short, a web security gateway performs URL filtering but does not examine the content of the packets. With the advent of telecommuting, remote access has become a common part of many corporate networks, especially today with the coronavirus pandemic. Today, many companies have employees who rarely if ever come into the corporate office. These users work at home or on the road. Even so, they still need access to corporate resources. This means opening access to more corporate resources for the internet than IT professionals want. The trick is to allow corporate employees the access they need, but to keep attackers out of these potentially open doors. Virtual private networks are a good way to increase the security level of data you transmit across the public data network. They normally use encryption to protect all the data they send between a user and the organization's network. Using a VPN for remote access provides security and is cost effective. The cost difference of using a VPN versus paying for a dedicated connection between two sites is significant. This figure shows an example of a VPN access to a network. VPNs require your gateway equipment to have a lot of processing power to handle the encryption algorithms. You can offload this processing power to another device by using a dedicated VPN concentrator rather than having your router or firewall terminate the VPN. In deploying a VPN, you must consider the security of the end user's computers. Once users connect to the corporate network, their PCs could be an open portal into those resources for an attacker who gains access to the PC. For this reason, many organizations require their employees install security software on their home computers. You can also limit VPN access to laptop computers your organization owns and manages. The three major VPN technologies in use today are as follows. You have point-to-point tunneling protocol, or PPTP. The point-to-point tunneling protocol was once the predominant VPN protocol. For many years, almost all VPNs use PPTP. It is easy to set up on client computers because most operating systems include PPTP support. Next, you have Secure Sockets Layer, or SSL. The Secure Sockets Layer encrypts web communication, and many VPNs use SSL to provide encrypted communication. Users connect to an SSL protected web page and log on. Their web browser then downloads software to connect them to the VPN. This requires no advanced configuration of the system. For this reason, SSL VPNs are quickly growing in popularity. Finally, you have IPsec, Internet Protocol Security. This is a suite of protocols designed to connect sites securely. Although some IPsec VPNs are available for end users, they often require the installation of third-party software on the user system and are not very popular. Many organizations use IPsec to connect one site to another securely over the internet. The required IPsec VPN functionality is built into many routers and firewalls, allowing for easy configuration. VPNs provide clear benefit to an organization. They offer an inexpensive, secure replacement for dedicated connections between sites. They also enable users to connect securely to the organization network from remote locations. This promises increased productivity because workers can easily get to resources they need while on the road. Network Access Control, or NAC systems, enable you to add more security requirements before allowing a device to connect to your network. They perform two major tasks: authentication and posture checking. Although NAC is a new technology, or rather new, it is growing in popularity. Many organizations now deploy NAC for both internal users and guests using their network. NAC works on wired and wireless networks. The IEEE 802.1x standard describes the most common NAC technology. Commonly referred to as simply 802.1x or 1x, this standard tells how clients may interact with the NAC device to gain entry to the network. Software on users' computers prompts them to log onto the network. After verifying the user's credentials, the NAC device instructs the switch for a wired network or access point for a wireless network to grant the user access to the network. This is the authentication component of NAC. Posture checking is an optional second use of NAC technology. When posture checking is used, the NAC device checks the configuration of the user's computer to ensure that it meets security standards before allowing it access to the network. Some things commonly checked include things like up-to-date antivirus software, host firewall enabled, operating system supported, and operating system patched. If users attempt to connect to a non-compliant system to a network, the NAC device offers two options. The administrator can decide to block such systems from the network until they are fixed. Alternatively, the system may connect to a special quarantine network where you may fix the system before gaining access to the main network. The Extensible Authentication Protocol, or EAP, is an authentication framework that defines the transport of keys and authentication credentials. EAP is commonly used in wireless network authentication. The Protected Extensible Authentication Protocol, or PEAP, PEAP, is basically EAP running in a TLS tunnel. PEAP provides more security than EAP for authentication exchanges. Wireless networks have become very popular for connecting devices within the home and office. Wireless networks can connect laptops, desktops, smartphones, and many other devices. Wireless networking allows users to work from any location in the building without worrying about finding a place to plug in a network cable. Configuring a wireless network is quite easy and it's inexpensive. The question becomes, what does wireless technology do to the security of your network? If it is so easy for an employee to connect to the network, does that mean that others can connect as well? Setting up a secure wireless network, at least one as secure as many wired networks, is possible. However, it takes careful planning, execution, and testing in order to do it. Properly configured, strong encryption is critical to operating a secure wireless network. In this section, I'm going to teach you some wireless networking technology, and you're going to learn how to configure and secure wireless networks. Let's look at wireless access points, or WAP. This is the connection between a wired and wireless network. WAPs are radios sending and receiving networking information over the air between wireless devices and the wired network. Anyone within radio range of a wireless access point can communicate with it and attempt to connect to the network. Attackers who want to undermine your security can do several things with a wireless network. First, they understand that wireless networking extends the range of your organization's network beyond your walls. While you can easily control physical access to a wired network, walls and fences don't stop wireless signals. Therefore, wireless networks without proper security present an easy target for attackers who want to connect to your network. Second, they know that it's much easier to eavesdrop on a wireless network than a wired one. It's very simple for anyone within radio range of your network to capture all the data sent on that network. If those data are unencrypted, they're fair game for an attack. Let's look at some wireless network security protocols. Fortunately, you can do quite a bit to secure your wireless network. In this section, you will look at several examples of wireless network security security controls. The most important is the use of wireless encryption to prevent eavesdropping. Other techniques to provide added security include disabling Service Set Identifier or SSID broadcasting, implementing MAC address filtering, and adding strong authentication to your wireless network. VPN over wireless. One of the most secure ways to implement secure wireless networks is to use VPNs for all wireless connections. This is easy to manage for internal users, but guest access to a VPN is more difficult. One common solution is to create at least two separate wireless networks. One network for internal users who require VPN access and greater connectivity into your internal network, and one network for guests that does not allow VPN access. The guest network also should have very limited connectivity to your internal network. Next is wireless encryption. Encryption is the single most important thing you can do to secure your wireless network. Encryption makes it impossible for an outsider to view information traveling over the network. Without encryption, all wireless users' activities are visible to anyone who comes within radio range of your network. It would be possible for an attacker to sit in the parking lot of your building with an inexpensive antenna attached to a standard laptop and monitor everything happening on your wireless network. You must use strong encryption. In the early days of wireless networking, the industry developed a standard called WEP, or Wire Equivalent Privacy, which provided basic encryption. WEP relies on the RC4 encryption algorithm created by Ron Rivas for RSA in the late 1980s. Since its release, security analysts have discovered significant flaws in WEP that makes it insecure. With software freely available on the internet, it is simple to break the encryption on a WEP network in a matter of seconds. In fact, using WEP on a wireless network is probably worse than using no encryption at all because it provides a false sense of security. People feel they are safe because their wireless network encrypts traffic. They don't realize they're using the equivalent of a Captain Crunch decoder ring to protect their data. Fortunately, there's an alternative to WEP. Actually, several alternatives were developed to address WEP's weaknesses. One is the Counter Mode Cipher Block Chaining Message Authentication Code Protocol, or CCMP. This is an encryption protocol that implements the 802.11i standard. CCMP provides enhanced security through the use of the counter mode of the AES standard. In addition to CCMP, the Wi-Fi Protected Access, or WPA standard, uses strong AES encryption to protect data on networks and does not share the same vulnerabilities discovered in WEP. WPA refers to the draft of the IEEE 802.11i security standard. This standard was intended to be an intermediate solution to the WEP vulnerabilities. WPA became available in 2003. The more secure standard WPA2 was available in 2004. This standard's official name is 802.11-2004. WPA and WPA2 is quite easy to configure. In their basic form, WPA and WPA2 require entering a shared secret key into the network configuration of every computer on the network. In more advanced forms, you can replace the shared secret key by giving each user a unique username and password. These passwords can be identical to the user's normal credentials by using a central authentication server, such as a remote authentication dial-in user service, which is called Radius, a Radius server. Radius was introduced in 1991 and quickly became a popular protocol to manage remote user connections. The protocol provides a central method to manage authorization, authentication, and accounting services, or the AAA services. Its successor, Diameter, was introduced in 1998. Recently, Diameter has become more popular for handling wireless remote connections since it has the ability to address more mobility issues than radius. For example, diameter includes better roaming support and can use TCP or SCTP protocols. Let's move to SSID broadcast. By default, wireless networks broadcast their presence in the public. They send out announcements containing the network's SSID. This is the public name of the network. You've seen these before when you boot up in a coffee shop, for instance, and your computer tells you that wireless networks are available. This notice includes the SSIDs of all available networks. You can stop your network from announcing itself by disabling SSID broadcasts on your wireless access points. If you disable SSID broadcast, users connecting to your network will need to know it is there and provide the network names themselves. This is fine if you have regular users, such as in a corporate environment. It will not work well if you allow guest access to your network. Finally is MAC address filtering. WAPS also enable you to apply MAC address filters to control which computers could connect to your network. With this technology, you provide a list of acceptable MAC addresses to your WAP, or wireless access provider. You should allow only approved computers to connect to your network. Deny all other computers access to your network. The major advantage of MAC address filtering is that it is very complicated to maintain. The major disadvantage of MAC address filtering is that it is very complicated to maintain. If you have more than a handful of computers on your network, it quickly becomes a major challenge to update the list of acceptable MAC addresses. Imagine if you work for an organization with 20,000 users. It wouldn't be unusual to see 100 new computers on the network every week. That's in addition to 100 dropping off the network as you replace them. Can you imagine trying to update 200 MAC addresses every week? Use MAC address filtering in cases where it makes sense. In addition to the preceding suggestions, considering the hardware In addition to the suggestions I already gave you, consider the hardware selection and placement of your wireless network devices. Selecting the right hardware and placing that hardware in the right position can have a noticeable impact on your network security. In particular, pay attention to these aspects of wireless hardware management. You have antenna types. Wireless device antennas can have a large impact on the device's area of coverage. Generally, external antennas can reach farther than internal antennas. Also, antennas can transmit and receive in different ways. They can be omnidirectional, which means all direction, semi-directional, which means limited direction, or highly directional, which is focused direction. Choose the right antenna for your organization's use. Next is the antenna placement. Once you select the best antennas for your devices, carefully place the antennas to provide coverage that you want and not for anyone else. Placing an omnidirectional antenna near an external wall will likely make your wireless network available to people outside your building. Next is power level controls. You can change the power a wireless device uses from the configuration settings. Lowering the power settings from the default will reduce the area the device covers. This setting can be helpful when attempting to limit the visibility of your wireless networks. Next is captive portals. A captive portal is a web page that is displayed for all new connections. Your wireless device can redirect all traffic to the captive portal until the connection is authenticated. The most common use of a captive portal is to provide a logon page for your wireless network. And finally, site surveys. One of the most important non-technical aspects to securing wireless networks is the site survey. Examine the physical area you want to serve with a wireless network. Facility floor plans can help you determine the best placement for your wireless devices. Use diagrams to plan your wireless network before you physically place devices. Although no network is totally secure, putting the right security controls in place can make your networks safer. The main point is never rely on a single control. Always use layered controls. You should always assume that a savvy attacker will be able to compromise one or more of the controls you have in place. Ensuring that an attacker must compromise multiple controls to get to your data is the best way to make your IT infrastructure as secure as possible. So in this lesson, I taught you about the Open Systems Interconnection, or OSI reference model, and how it serves as an example of how you can build and use a network and its resources. You learn about network layer protocols, including an overview of TCP/IP. You learn some basic tools for network security. You also learn how wireless networks work and what threats they pose to the security of your organization. Finally, you gain a better understanding of the need for security policies, standards, and procedures, as well as how your IT infrastructure is only as secure as its weakest link. I'll see you in Lesson 11.